Okay, so this is going to be a brief introduction to vectors here. So a vector is a quantity in math and physics that involves both a magnitude and a direction. So examples of a vector would be, for instance, velocity. Velocity is a vector because not only is there magnitude, how fast an object is moving, but a direction. What direction is an object moving? Okay. Another vector would be displacement, which is the change in an object's position. So not only is there a magnitude, how far an object moved, but what direction did an object move in. And the one we're going to work with a lot in this section is force. So that would be like pushing an object, of course, with a certain magnitude, but as well in a direction. Okay. In contrast, a scalar is a quantity involving only magnitude. So as an example, that would be, say, temperature. The temperature of a room could be 70 degrees, but there's no direction, it's just 70 degrees. Another one would be mass. The mass of an object is just what it is. There's no direction involved. Also, speed, which is like velocity, but without the direction. So it's just the intrinsic speed of an object. And same with distance, which is just regarded as like a general notion of length, compared to displacement, which has a direction associated with it. Okay, so why is this a trigonometry topic? Well, because of that direction for vectors. So vectors can be very well represented as arrows graphically. Okay, so for instance, the direction of the arrow, of course, comporting with the direction of the action, whether it's a force or velocity or whatever, and the length of the arrow representing the magnitude. So this might be, for instance, a 30 Newton force in that direction compared to half that length, 15 newtons, but also in that direction. Okay, and if you can imagine an object with, say, both of these forces acting on it. So let's say we have an object here and somebody's pushing 30 newtons in that direction, and then another person is pushing 15 newtons in that direction. This is a trigonometry problem because you can imagine that the object itself will accelerate probably some angle between them, right? So maybe something like this in that direction, and closer to the 30 than the 15 because the 30 is stronger, right? And so perhaps this will move in, say a direction like this. Okay. And that is called a resultant vector. And the exercises we're going to see in this section will basically amount to just finding resultant vectors given a particular situation. And you can imagine that we will solve this using the law of cosines and law of sines because we're going to be building triangles out of these arrows. Okay. Before we get into our first example, though, there's one more definition here. And the opposite of a resultant, which we're also going to be looking for, is called an equilibrant. Okay, you can think of the equilibrant as the magnitude and direction of the force somebody would have to apply kind of in the opposite direction, right? That would prevent the object from accelerating. So again, if you had somebody pushing a 30 Newton force in that direction and a 15 Newton force in that other direction, the equilibrant would be the magnitude and direction that somebody would have to push, a third person would have to push in order to counteract the other forces to prevent the object from accelerating. Okay. So, okay, well, how do we actually calculate these things? Well, it's pretty straightforward. In order to find an equilibrant, first of all, you should just find a resultant and then point it in the opposite direction. So I'm just going to show you how to find a resultant. And to find the resultant, what you do is you add the two vectors. Okay, now what does that mean? Well, let me show you with a new example here. So let's suppose we have an object here, and we have a particular vector, we'll call it v1, pointing in that direction, and we have a particular vector v2 pointing in this direction. Then what you do to find the resultant is you take a copy of either v1 or v2 and you paste it at the end of the arrow of the other vector. So I'm going to take v2, for instance, and I'm actually literally going to copy it and paste it right there at the end of v1. And our resultant will be the vector that starts at the beginning of v1 and now ends at the end of v2. So we get our magnitude and our direction out of this. Okay, and as you can see, it's definitely a trigonometry problem, typically law of cosines and law of sines, to get the different measures that we need. Okay, so alternatively, you could have taken v1 and pasted it at the end of v2, and you would have still arrived at the same resultant vector. So it doesn't actually matter which one you pick up and move to the other end. Okay. The equilibrant, once you find the resultant, of course, the equilibrant will be just the opposite direction with the same magnitude. All right, so let's look at some examples. All right, so here we have an object with two different forces acting on it, and we are interested in the magnitude and direction of the resultant. So let's draw a quick diagram. We have, say, our object here, and there's a 19 Newton force. So Newton, by the way, is the unit of force denoted by capital N in the SI or metric system. Okay. In the US system, we use pounds typically to measure force. Let's say that's the 19 Newton force. Okay. And now we can draw the 32 Newton force with an angle of 118 degrees from the 19, pretty much anywhere you want, as long as there's an angle of 118 degrees. So because I drew the 19 there, which wasn't a great spot to start, but so this is perpendicular to that 19, and 118 is a little bit more than perpendicular, so maybe something like this. Okay, and 32 is about that long relative to 19, maybe a little bit longer. So something like that. So we'll call that the 32 Newton force. Okay, and this angle between them is 118 degrees. Again, the orientation of the diagram, like you could have rotated this or you could have drawn, probably would have been easier just to start with the 19 at level and then swung out from standard position 118 degrees on the 32 and maybe drawn it like that. Okay, so very good. So now let's draw our resultant. So all you have to do is take one of these vectors and move it so that the tail of that vector is on the tip of the other vector. So I'll move the 19 and we'll put it at the end of the 32 here. So it's about like so. Okay, and our resultant vector is going to be that guy. So that's the vector we're interested in. We not only want to know its length, but its direction. And of course, when we give its direction, we're really just going to find, say, the theta right here. And we're going to say, well, it's however many degrees away from the 32 Newton force. Okay. All right, so let's call its length x, and we do have a triangle to solve. And while it may look like it is a right triangle. You can't take that for granted, so you can't just use SOHCAHTOA to solve this. We're probably going to need the law of sines or cosines. And great, so we want x, we also want theta, but we don't even have any angles in this triangle right away. However, we can find this angle right here. Let's call it alpha. Okay, and let's note that since these two 19 Newton forces are parallel, alpha and 118 degrees are supplementary. So now, this is an old theorem from geometry. Let me draw the situation here. If you have two parallel lines and a line between them, which is called a transversal, okay, then this angle right here is supplement to that angle right there. Okay, meaning they add up to 180 degrees. So we know to find alpha is 180 degrees minus 118. And this is probably a move you're going to need to use to start all these problems. Okay? So 180 degrees minus 118 degrees is 62 degrees. So alpha is 62 degrees. All right. Now, we do not have an angle and opposite side pair in this triangle. However, we do have two sides and the included angle, which is alpha, which means we can use the law of cosines to find x. So we now know, so x squared is 32 squared plus 19 squared minus 2 times 32 times 19 times cosine of alpha, which is 62 degrees. So I get that x squared is 814.123 square newtons, kind of a meaningless measure for now, but we'll take the square root of that, and I get 28.5328 newtons. Okay, and looking at our diagram, I would accept 28.5328 as an approximate length for that, given the dimensions in that diagram. Okay, so of course when we present our final answer, we'll round that to the significant figures in the problem, so that would be 2, which means we'll say it's 29 newtons, but we also need to find that theta, okay? And now that we have alpha and x, we have an angle and opposite side pair, and we have the side opposite theta, so we can use the law of sines to find theta. So we can see from our diagram that sine of theta divided by its opposite side, which would be 19 newtons, I'll leave the units off, is equal to sine of alpha, that's 62 degrees, divided by x, which is 28.5328 newtons. So sine of theta is equal to 19 times sine of 62 degrees divided by 28.5328. We'll do that calculation. So I get that sine of theta is 0.587954. And therefore, theta will be the inverse sine of that. And I get 36.012 degrees. Okay, remember, don't round any numbers until you're actually presenting your final answer. So again, looking at the diagram, I would accept that theta is 36 degrees, right, approximately. Good, so let's present our answer. Now, notice that when we present it, we need to actually give some sort of a reference, so we'll refer to theta as being off of the 32 Newton force. The resultant force is 29 newtons in a direction of 36 degrees from the 32 Newton force. All right, very good. Okay, so here we have two rescue boats pulling a broken boat with forces of 840 and 960 pounds. And they're pulling in mostly the same direction, but there is a slight angle between them of 24 degrees. And this time we want to find the magnitude and direction of the equilibrand. Okay, so that's the exact opposite of the resultant. But in order to do that, we need to actually find the magnitude and the direction of the resultant, and then simply just move the arrow to the other side. So let's see what I mean by drawing a diagram. So let's say this is our boat that's being rescued, and let's just suppose that that first tugboat is pulling with, say, a force of 960 pounds. So let's just draw its vector, and we'll call that 960 pounds. Then at an angle of 24 degrees from that in any direction you want, we have another one pulling at 840. So that's going to be basically a slightly smaller arrow and at a 24 degree angle. So maybe something like that. All right, and that's an angle of 24 degrees between them. So first we're going to find the resultant and then worry about the equilibrant after that. And of course we're going to take one of these arrows and just slide it over to the other arrow. So we'll take the 840 for instance, and we'll just sort of paste it right here. Okay, and that means that our resultant vector is going to be right through here. Okay, so that's what we're after. We're after that length. The length of that, which we'll call x for now, is going to be the same length as the equilibrant. So we can say the magnitude of the equilibrant will be whatever x is. The direction of the equilibrant is exactly the opposite here. Okay, so, and it'll have the same length. So once we find the direction of the resultant, okay, which will be, say, this angle right here, then you can see that the supplement of that angle will be the direction of the equilibrand. Okay. All right, so let's call this angle theta in there. And for most of this problem, mechanically, it's very similar to the last one. We're going to find our x, we're going to find our theta. Okay. All right, so we need to solve this triangle here, and of course we're going to need an angle, and we haven't factored in this 24 degrees yet. But based on the same reasoning as last time, we know that this angle right here is the supplement to 24 degrees. So that angle is going to be 180 degrees minus 24 degrees, okay, which is 156 degrees. So now we can use the law of cosines. Okay, so we know that x squared is 960 squared plus 840 squared minus 2 times 960 times 840 times the cosine of 156. So I get that x squared is 3,100,566.114 blah blah blah, and that's square pounds. Okay, so of course we'll take the square root of that, and I get that x is 1,760.84 pounds. All right, so that is the magnitude of our resultant, and of course, therefore, that'll be the magnitude of the equilibrand. So now we should find that little theta, which is going to be the supplement of the angle of the equilibrand. So we can see that sine of theta divided by its opposite side, which is the 840, is equal to the sine of 156 divided by its opposite side, which is that x we just found, 1760.84. This is, of course, using the law of sines. So now we'll just solve for sine of theta and then take the inverse sine. So I get sine of theta is 0.194031. And so theta is the inverse sine of that. And I get that theta is 11.1881 degrees. All right, looking at our diagram, you can see, yeah, it's sort of about half of the 24, but not quite. It's a little less than half, right? Because there's some bias toward that 960-pound force, right? That one's pulling more than the 840 is. So the resultant vector will be closer to the 960 than it is to the 840. So don't make the rookie mistake of just dividing 24 by 2 and saying, well, that's a 12-degree angle. Because look, it's smaller than 12. It's 11.18, blah, 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 right? Of course, what are we really after? Let's call this, let's call this angle gamma. Okay, we're after gamma, which is the supplement of theta. So I get that gamma is 168.812 degrees. All right, so now we have the magnitude of our equilibrant and its direction. So we can answer the question. The original measures were given in two significant figures for the pounds. So we're going to say that this is 1800, rounding 1760 all the way up to two significant figures. Whoops, these were in pounds, not newtons. Okay, and to be specific for the direction, we said it's 169 degrees away from the 960 Newton force, because that was our reference force for that 169 degrees. Okay, so here we are interested in finding the angle between two forces, and we actually know the magnitude of the resultant force. So let's see what we've got. We have, say, an object here and two forces. We do not know the angle between them. So we do know that one of the forces is 253 newtons, and then another force is 128 newtons. So that's about half the other one. Okay, and I'm just going to guess that maybe that's a good diagram, although we don't know the angle between them, so maybe they're very close together, or maybe they're very far apart. Okay, however, we do know the magnitude of the resultant. So we can demonstrate that in our diagram by taking one of the forces, like the 128 Newton, and moving it over here, and then drawing our resultant, which we know to have a magnitude of 320 newtons. Okay, now what are we after? We're after this angle right here, which we'll call theta. Okay, and we do know that the angle right here, as usual, is the supplement to theta. We'll call it alpha. All right, which means that if we can find a way to learn what alpha is, well, then we just subtract it from 180 and we've got theta and we're done. Okay. And if you recall in the last section on the law of cosines, when you were given three sides of a triangle, as we are here, but no angles, you do need the law of cosines to find that missing angle. Okay, and specifically, when we're setting it up, the side that's opposite that angle is the side that's isolated in the law of cosines, which means it's the 320 that'll be squared on the outside, and then there'll be a 128 squared plus 253 squared minus 2 times 128 times 253 times cosine of alpha, and it's that alpha that we're after. Again, let's be very, very careful with this calculation and do it in steps. So the first thing I'll do is 2 times 128 times 253, and I get 64,768. Then we'll do that calculation there, 128 squared plus 253 squared, and I get 80,393. And 320 squared, which is 102,400. Okay, now we can subtract the 80,000 figure here from the 102,000, and I get 22,007 is equal to negative 64,768 cosine of alpha. Then we can divide both sides by negative 64,000. So we get cosine of alpha is equal to, I get negative 0.339782. And so alpha will be the inverse cosine of that figure. Okay, something interesting here is because we're taking inverse cosine of a negative, and we know how inverse cosine works, this is going to generate a second quadrant angle, which is exactly what we would want, right? We clearly, that angle was obtuse in our triangle. It was a very large angle, greater than 90 degrees. So this is a situation showing, again, why inverse cosine would be defined in that particular way. So I get theta equaling 109.864 degrees. If you look at our diagram, indeed, we do have a second quadrant angle there, right? It's obtuse. It's bigger than 90 degrees, less than 180. And that's our 109. Now, what are we after? We're after what theta was, which is the supplement of that. So I get 70.1364. All right. Now, significant figure rules for angles are a little bit tricky. We'd be safe just saying 70 degrees, rounding it to two significant figures, with that 0 actually being significant. But I'll put a little period right there to indicate that that's precisely 70 and not rounded from, say, 69 or 71. Okay, so there it is. That's the course content for Math 124.